On November 21st, 2021, a spacecraft traveling at 364,000 miles per hour made history in a way that almost nobody registered. It didn't land on anything. It didn't take a famous photograph. It didn't carry a human being. What it did was pass through the outer atmosphere of a star, our star, the Sun. For the first time in history, a human-made object touched the Sun and survived. And what it found inside contradicted models physicists had spent 70 years building. The lead researchers described the data as, in their words, rewriting our understanding of the heliosphere from the inside out. Almost nobody talked about it. The Parker Solar Probe launched in 2018, named after astrophysicist Eugene Parker, who in 1958 first proposed the existence of the solar wind, the continuous stream of charged particles flowing outward from the Sun in all directions. The mission was designed to answer questions that had been accumulating since the dawn of the space age. Why is the Sun's outer atmosphere millions of degrees hotter than its surface? Why does the solar wind accelerate as it moves away from the Sun rather than slowing down? Where do solar flares and coronal mass ejections originate, the ones that can disable satellites, knock out power grids, and in the right circumstances cause a geomagnetic catastrophe that civilization-scale infrastructure is almost entirely unprepared for? Parker went to the source. It flew closer to the Sun than any spacecraft in history, reaching approximately 3.8 million miles from the solar surface. Mercury, the closest planet, orbits at 36 million miles. Parker flew nearly 10 times closer than Mercury. It flew into a region so hostile that its instrument package sits behind a carbon composite heat shield 4.5 inches thick, withstanding temperatures approaching 2,500 degrees Fahrenheit on its sun-facing side, while the instruments behind it operate at room temperature. And what it found inside that furnace changed the picture entirely. Let me give you the metaphor that carries through all of this. Think about studying an ocean from the shore. You can watch the waves, measure the temperature, track the tides, build a reasonable model of how it behaves. But until you go into the ocean, there are things you simply cannot know. The structures that form beneath the surface, the way energy moves through the water column, the mechanisms driving the currents you can see from the beach but whose origins lie far below in conditions you've never directly observed. Every piece of solar science done before Parker was done from the shore. Parker went into the ocean, and the ocean turned out to have structures the shoreline observations never revealed. Start with the oldest and most frustrating mystery in solar physics, the coronal heating problem. The surface of the Sun, the photosphere, has a temperature of approximately 5,500 degrees Celsius, hot by any earthly standard. And yet, the corona, the Sun's outer atmosphere extending millions of miles above the surface, has a temperature of 1 to 3 million degrees Celsius, in some regions even hotter. The surface is 5,500 degrees. The atmosphere above it is 1 million degrees. This is physically backwards from everything thermodynamics suggests. Walk away from a campfire and you get colder. The Sun's corona does the opposite. It gets orders of magnitude hotter as you move away from the surface. For 70 years, despite the best efforts of some of the most capable physicists on Earth, nobody had a fully satisfying, observationally confirmed explanation. Parker got close enough to find one, or at least to find the shape of one. What it detected was not a clean confirmation of any existing theory. It found both wave activity and small-scale explosive energy releases just above the Sun's surface, but it also found something largely unexpected: sudden, intense velocity spikes in the solar wind plasma, localized bursts. The material was moving dramatically faster than its surroundings. These spikes, when mapped back to their origin points, appeared to coincide with rapid, violent rearrangements of magnetic field lines, places where the magnetic geometry was reorganizing itself and releasing energy in the process. The picture emerging from Parker's data is that the corona is heated not by one clean mechanism, but by a turbulent, multi-scale cascade. Magnetic reconnection events at many scales, wave dissipation, impulsive heating, all operating simultaneously. The corona is not a passive atmosphere. It is an extraordinarily dynamic, magnetically complex environment in constant energetic upheaval. And understanding that upheaval is the first step toward actually predicting when the sun is about to do something violent, which matters for reasons we'll get to in a moment. But first, let me tell you about switchbacks, because this is the Parker discovery that genuinely surprised everyone, including the people who designed the mission. As Parker flew through the inner heliosphere, its magnetometer began detecting something strange. The magnetic field lines in the solar wind, expected to point in a relatively consistent direction as they spiral outward from the sun, were flipping. Suddenly, abruptly, reversing direction by 180 degrees, then reversing back. The field would be pointing outward, then in seconds it would be pointing back toward the sun, then outward again. These S-shaped kinks in the magnetic field were happening constantly throughout the inner solar wind. Nobody predicted them. The researchers called them switchbacks, and they immediately raised a fundamental question. Where do they come from, and what do they mean for how the solar wind works? Two theories emerged. Either switchbacks form in the corona itself, generated by the turbulent magnetic activity that heats the coronal plasma and propagate outward, or they formed further out, through velocity shear between faster and slower solar wind streams, the way wind creates waves on water. Parker's subsequent close passes have increasingly pointed toward a coronal origin. Switchbacks appear to be born near the sun. Here's why that matters. If switchbacks originate in the corona and carry energy outward, they may be one of the mechanisms accelerating the solar wind. The solar wind starts slow near the sun and reaches hundreds of miles per second by the time it passes Earth. What accelerates it has been another long-standing mystery. The energy released as switchbacks form and propagate could finally explain the velocity profile observations have measured for decades without being able to account for. Parker didn't solve this completely, but it confirmed the phenomenon is real, pervasive, and almost certainly important. Now let me talk about the thing with the most direct relevance to your actual life, the thing that should be generating urgent policy attention and largely isn't. On September 1st, 1859, the most powerful geomagnetic storm in recorded history struck Earth, the Carrington Event. Telegraph systems around the world failed. Some operators received electric shocks. Telegraph papers caught fire. Aurora Borealis was visible as far south as Cuba. In 1859, those were the consequences. Telegraph networks temporarily disrupted, a spectacular light show at unusual latitudes. Run the Carrington Event through today's infrastructure, and the consequences are not whimsical, they are civilizational. A geomagnetic storm of Carrington magnitude would induce massive electrical currents in long conductor systems. The large, high-voltage transformers at the backbone of national electrical grids would be at serious risk of catastrophic failure. These transformers are custom-built, weigh hundreds of tons, are manufactured by a small number of facilities globally, and have replacement lead times measured in months to years. If a Carrington-level event destroyed a significant fraction of North America's grid transformers, restoration would not be measured in days. It would be measured in months, potentially over a year in the most severely affected regions. The downstream consequences are not limited to inconvenience. Water treatment is electrically powered, fuel distribution is electrically powered, food cold chains are electrically powered. Hospital backup generation is typically designed for days, not months. The scenario is not a power outage in the way most people imagine. It is the removal of the foundational infrastructure layer that everything else in modern society depends upon for a duration no society has experienced since that infrastructure was built. A 2008 National Academy of Sciences report estimated economic damage from a Carrington-level event at $1 to $2 trillion in the first year, with full recovery potentially taking 4 to 10 years. And how likely is such an event? Researchers analyzing ice cores have found evidence that events of comparable magnitude have occurred multiple times in the last several thousand years. A 2012 study estimated the probability of a Carrington-class event in any given decade at approximately 12%. By any insurance or risk management framework, 12% per decade demands serious mitigation planning. Here's where Parker's science connects directly to this risk. Current geomagnetic storm warnings are limited to roughly 1 to 3 days of advance notice because we detect coronal mass ejections primarily after they've already left the sun. By the time we see a CME, it's traveling toward us at 500 to 3,000 kilometers per second. 1 to 3 days is not enough time to safely protect major grid infrastructure. Parker's direct observations of coronal activity, its measurements of the magnetic field configurations that precede major eruptions, and its data on early CME development close to the sun are feeding into the next generation of solar weather prediction models. The goal is to extend reliable warning times to 5 to 7 days, which is enough time to take meaningful protective action if the procedures are developed in advance. The science is advancing. The policy and infrastructure hardening work is not advancing at anything close to the same pace. Parker uses Venus flybys to gradually reshape its orbit and bring it closer to the sun on each pass. By its closest planned approach, it will be traveling at approximately 430,000 miles per hour, nearly 3 times faster than the previous fastest human-made object ever. At these velocities and distances, its instruments are detecting phenomena that simply couldn't be resolved from further away. Magnetic field structure at scales of kilometers in a plasma spanning millions of kilometers. Acoustic signatures of processes theorized for decades but never directly measured. Early acceleration signatures of solar energetic particle events caught close to the sun where their properties reflect the acceleration mechanism itself. There's a companion mission adding a crucial second perspective. The Solar Orbiter, a joint ESA and NASA mission, is approaching the sun from an angle that allows it to observe the sun's polar regions in ways never previously possible. The sun's poles are theoretically important for understanding the 11-year solar cycle that drives variation in solar weather. No spacecraft has ever had the orbital geometry to observe them directly until now. Together, Parker and Solar Orbiter are giving solar physicists simultaneous, multi-point, direct observations of the inner heliosphere that are producing a three-dimensional picture of the sun's influence environment, qualitatively different from anything built from more distant observations. Eugene Parker published his theoretical prediction of the solar wind in 1958 in the Astrophysical Journal. It was initially rejected by reviewers as too speculative. The editor overruled them and published it. Parker was 31 years old. He spent the following 60 years watching the theory he proposed as a young man be progressively confirmed, culminating in 2018 when he watched, at age 91, as a spacecraft bearing his name launched toward the star his theory had helped decode. He was the first living person to have a NASA spacecraft named after them while still alive. Parker died in March 2022 at age 94. He did not live to see the full data set from his spacecraft's closest approaches, but he lived to see it enter the solar corona and survive. He lived to know that the instrument sent to the star he spent his career understanding had already discovered phenomena nobody had predicted. 60 years between the question and the instrument capable of testing the answer. The instrument is still returning data. What does Parker's solar probe ultimately tell us? It tells us that the nearest star to Earth is more complex, more dynamic, and more surprising than 70 years of remote observation revealed. It tells us that the physical processes governing stellar atmospheres operate through mechanisms we are only now beginning to understand at the level of direct measurement. It tells us the sun periodically does things that modern civilization's infrastructure cannot withstand, and the science needed to predict those events is advancing, while the preparedness to survive them is not. And it tells us something more general that I keep coming back to whenever I spend time with this material. Every time we have built an instrument capable of going somewhere new, operating in a regime no instrument had previously accessed, and returning direct measurements from that environment, we have found reality at that scale was more interesting and more complicated than we modeled from further away. This has been true from the first telescopes to the first spacecraft to the first planetary probes. It is true again with Parker. We don't yet have a complete theory of the solar corona. The Switchbacks don't have a fully resolved origin story. Parker has not closed the questions it was sent to investigate. It has sharpened them, narrowed the range of acceptable answers, produced observational constraints that theoretical models now have to satisfy, and revealed new questions that didn't exist before the data existed. This is what good science does. It doesn't produce a final answer. It produces a more precise question, and the more precise question is always more interesting than the vague one it replaced. Parker's solar probe will continue orbiting the Sun, continuing to set speed and proximity records, continuing to return data from the most hostile environment any human-made object has ever operated in, until its fuel is exhausted and its systems eventually fail. When that happens, it will orbit the Sun permanently, a small metal artifact tracing its elliptical path around the star its instruments spent years probing. We sent a probe into the Sun. It survived. It's still talking to us, and the Sun turns out to be stranger and more extraordinary than we knew. 3 takeaways. 1. The coronal heating problem remains unsolved, but Parker has provided the first direct measurements of the heating environment, pointing toward a multi-mechanism picture involving wave dissipation and impulsive magnetic reconnection events that remote observation could never have resolved on its own. 2. Switchbacks, the entirely unpredicted magnetic field reversals Parker detected throughout the inner heliosphere, appear to originate in the corona and may be a key mechanism in solar wind acceleration. They are exactly the kind of discovery that only direct measurement produces. 3. The risk of a major geomagnetic storm to modern infrastructure is real, documented, and chronically underestimated. Parker's science is building the foundation for better solar weather prediction. The gap between that science and institutional readiness to act on it is one of the most consequential, unaddressed risks in contemporary civilization. The Sun doesn't care about our timelines. The probe went in. The Sun surprised us. It always does.